Well, hi everyone. Welcome to our Management Science course, Chapter 11. This is a long chapter, but it's very practical, very applicable to the real world because we almost all of us certainly spend some time waiting in line or experiencing a queue that is a waiting line that is maybe perhaps when we connect through our web browsers or through our phones to the internet. You may or may not realize it, but you're waiting in a line, if you will, to talk to the server. Anytime we come in and out of a big facility that we are with a lot of other people, we go through airport screening. You certainly would be familiar with that if you travel through airports. If you drive, you wait at a traffic light and a queue forms. If you make a phone call for a customer service, there's an estimation in some organizations will give you that'll tell you your call will be answered in X minutes or so on and so forth. So it happens in many, many places in our life. So what do we want to learn about that? We want to learn how to manage them. And there are lots of software products that are in the commercial and industrial marketplace that will help manage your queues. We're going to use the Excel tool as a means by which to come up with some answers, but these higher order software products are much more flexible and powerful, but the basics can be obtained using Excel. So I'm just flipping through some of these other types of software and hardware solutions that are used to help manage queues. And so let's get down to the particular matters here with this chapter. Definitionally speaking, we call the study of waiting lines queuing theory. And it's a field of study unto itself. It's quite extensive. It's relatively active in the real world in terms of research. And we study, in this case, we're going to be concerned with four principal characteristics of a queuing system. First is their arrival rates, the manner in which they arrive. Second thing we're going to be concerned with are the service rates, the time required for a conduct service. That is, complete a transaction or whatever it is that's necessary. The third thing we're going to study is the order of service, what we call the queue discipline. And lastly, what we need to be aware of are the configuration of servers, whether physical or electronic, machines, whatever it might be, the number of them and their configuration. So, what do things look like when we have certain types of configurations? A basic indication would be single service channel or multiple service channels when a customer arrives or a request is made from a browser or a device to a server. If there's one server or one system and everyone goes in a single line, this is what it looks like. And we refer to this as one channel and when there is one server. And the designation that we use, the variable we use to designate a channel is K. We'll explain a little bit more of that in a bit. And then also the very configuration would be multiple service channels, whether it be 2, 3, 4. In this particular example, it's 3. And perhaps you see these at banks or when you wait in a queue to be called for service in some fashion. So again, that K number for multiple service channels can vary. And we use a different template or a different model in Excel when K is 1 or K is greater than 1, when it's 2, 3, etc., etc. We'll get back to that again as well. So in terms of queue discipline, we are going to focus only on first in, first out, or first come, first served, and not use the discipline of last come, first served. An elevator could be an example of that, where there's no guarantee because you got on first at a lower floor, let's say if you're going up, that you're going to get off first. So that differs. That is not a guarantee of first in, first out. So when we distinguish through notation for these different queuing system designs and configuration, we use a three-part code. And we identify, I'm going to call these variables A, B, and K. It's something that's called Kendall's notation. Kendall was a British mathematician. And A is used to identify the distribution form of arrivals. B is used to, the second variable is used to identify the distribution of the departures, and K is the number of channels. So we replace the A variable with an M, pardon me, A or B variables with either an M, a D, or a G, where we have, for M, we have a Poisson or exponential distribution for that arrival or distribution or completion rate. Or we say D when we have a constant value, or we say G when we have something with a known mean and variance. So when we say an MMK model, we say it's a Poisson distribution with a service time following an exponential distribution, and there are K servers working at identical service rates. Okay, so something else that we are a premise for our work is that we are working on the basis of what we call a normal or steady state of operation. In practical terms, in a queuing system, there's a startup period when the queue builds. It's referred to as the transient period. Now, the transient period ends when there's a steady state of operation. The waiting line models we're going to deal with reflect the characteristics of a steady state operation. No variation. Now, again, when we think about the inputs to the queuing models and the templates in Excel that we're going to use, we most particularly want to be concerned with the arrival rates and the service rates. Now, those arrival rates, again, we think of them generally as a random event. We model them using a Poisson probability distribution, depicted graphically here. With service times or throughputs, we also use those that are represented in a random fashion. We assume for the most part with an MM, they are given as an exponential distribution. Now, symbology is important here because we're going to use 3 distinct Greek letters in our symbology. For the arrival rate, we use the Greek letter lambda, if you will, for an L, Greek letter for L. Service rate, we're going to use the Greek letter mu. This would be the Greek letter for M. And in some cases, a limited number of them, we also use the Greek symbol for sigma, for S, which is the standard deviation. So that will only apply to one of our cases. Arrival rates and service rates are very important for us to be able to understand. Now, here's something definitionally we want to make sure we know. Again, lambda is the average arrival rate. Lambda is associated with arrivals. We can also flip that around and say 1 divided by lambda is the average time between arrivals. Mu, again, mu is the average service rate for each server. We could flip that around and develop an average service time. And sigma is the standard deviation associated with that service time. Please take note on these for definitional purposes. So if you're going to follow along, I encourage you to get Excel on your computers as well. So these are the types of models that we're going to study with first come, first serve. Using Kendall's notation, we're going to study in MM1 models, MMK, MD1, MG1, and MM1 with finite calling population, we call that an MMF, as in Frank. We're also going to study economic analysis of waiting lines, and some part of all of these are going to be part of the Chapter 7 test. Okay, so when I use, say, MM1, MMK, MD1, MG1, MM1F, I want you to understand that these are the models we're referring to. Okay, so let's talk about an MM1 system first. Go through some simple examples. All right, so let's go through this example, an MM1 queuing system, where Joe Ferris is a stock trader at the stock exchange. So the transactions arrive at a mean rate 20 per hour. So let's understand that to be mu. Each order requires an average of 2 minutes to process. Assume they're continuous. So let's get familiar. What is mu, the service rate, expressed on an hourly basis? Here's the key to this, and I want you to really grasp this and take your time and use the practice problems to understand. These two data points are given to you in different units of time. This is expressed on a per hour basis. This is expressed in terms of duration, taking 2 minutes. That is not 2 per hour. Right? So we have to convert that. How many orders can he process in an hour? We want that to be common units. So if it takes 2 minutes to process an order, then Joe can process 30 per hour, right? 60 minutes per hour divided by take 1 being done in 2 minutes. So you've got to make sure you work in common units for everything. You're going to often have to convert some input values to some common units. All right, so let's look at something else. Let's look at a different in terms of those arrival rates and what's it look like and probabilities and so on. So for Joe, what's the probability that he doesn't get any orders within a given 15-minute period of time? Remember that they arrive at a mean rate of 20 per hour, but because they're done in a Poisson distribution model, it's conceivable that for some period of time there are no arrivals. So the orders arrive at a mean rate of 20 per hour. If we convert that, that becomes 1 order every 3 minutes in average. Therefore, in a typical 15-minute interval, the average number of arrivals should be approximately 5 on average. So we use this formula given here to calculate that. So when we decide that we're going to ask the question, what's the probability, P, of X being 0, we take this calculation. We use lambda. Lambda is 5, as we just derived. That would be typically expected to be 5, to the x power. X is 0, so to the 0 power, times e, which is a mathematical constant, equal to 2.718. So when we want to calculate e to the negative lambda power, we use that in Excel. We can use the formula equals 2.718 shift 6, or the caret symbol, x. So when we do that, in this case, 5 to the 0 power, any number to the 0 power is 1. And we also divide this by a factorial. Now, again, for the value of x, again, we can calculate that in Excel using the formula equals FACT parentheses the given x value, whether it's 0, 1, 2, 3, 4, and so on. Now, also, any number, if 0 to the 0 factorial is also equal to 1. So when we reduce this expression, we get e to the negative 5th power. If we use that calculation, we're 2.718 shift 6, negative 5, we get this number, 0.0067. Converting that to a percentage, if you will, would be 0.67%. And that's how we would calculate this type of problem. So it should make intuitive sense to you that if we typically have 20 orders arriving per hour, and if I ask you what's the probability that within a given 15-minute period of time nothing arrives, it's going to be a pretty low number. So it's less than 1%. Let's consider a different x number. What's the probability that 3 orders come in a 15-minute period of time? So the same equation is used, but x is equal to 3. So in that case, we have different values. So we have to calculate 5 to the 3rd, which is 125. E to the negative 5th, which is this value, and that would then 3 factorial, which is this value, 6. We do the math there, we get 13.96%. All right, makes a little more sense. We get typically, every 1 order every 3 minutes. 3 orders in a 15-minute period of time, it's going to be a little lower, than that. Seems to make sense. So let's look at another practice problem. And the answers to these practice problems are given to you in a file that I posted as well. So during summer weekdays, some boats arrive at a drawbridge and so on. A Poisson distribution rate of 3 per hour. In a given 2-hour period, what's the probability that none arrive, that 2 arrive, that 8 arrive? So in that case, we're using the same formula. We have x equal to 0. Do the calculation, x equal to 2, do the calculation, x equal to 8, do the calculation. Should be very simple and formulaic for you to follow this. Okay, we're going to stop here and I'm going to go into the next recorded segment. So come back at the next recorded segment to pick up on this page.